Hello dear students, today's video session is about subtopic number 4.2 of subject Electrical Instrumentation, which is calibration of ammeter, voltmeter, wattmeter and single phase energy meter along with adjustments as per the Indian standards, that is IS. Now first we shall see what are the outcomes or what will be the outcomes of this session. After this session, the students, that is you will be able to calibrate various electrical instruments, namely ammeter, voltmeter, wattmeter and single phase energy meter. Now, before we proceed further, let me brief you about calibration. What actual calibration is. Calibration is the process or method of finding or calculating the percentage error at different scale readings of any electrical instrument. Say for example, we have an ammeter. It has been connected in a circuit. Now what the reading of ammeter is shall be treated as measured value of the electrical current passing through the circuit, that is IM, measured value. Now suppose the ammeter has some error due to which it shows a reading which is slightly higher or lower than the actual value of current passing through the circuit. So the actual value of current passing through the circuit is IS, true value of the current passing through the circuit. So the difference between IM, measured value of the current, and the true value of the current passing through the circuit is known as error. That is, error is IM minus IS. This error, when divided by true value, that is IS, whole multiplied by 100, will give us percentage error. So this is what calibration is. Now basically there are two methods of calibration. The first one is calibration using a potentiometer, and the second one is calibration using another meter which is known as substandard meter or standard meter or reference meter. The first method of calibration, that is using a potentiometer, has already been covered in second chapter of this subject, so I won't be discussing it again. We shall move to the second method. Now let's start with calibration of ammeter. As you see in the circuit, there are two ammeters which are connected in series with the load. Now this load is a variable load because we need to take minimum 5 readings of the test ammeter as well as the substandard ammeter. Now the first ammeter is test ammeter, which means the ammeter which needs calibration, which has to be calibrated. The second ammeter is the substandard ammeter or reference ammeter or standard ammeter, which is used for calibration of the test ammeter. Now we shall proceed with the process of calibration. Now the load is so varied that the current as shown by the test ammeter is equal to its maximum scale mark, or you can say it as full scale reading. For example, if you have a test ammeter of range 0 to 10 amperes, then we shall vary the load till the test ammeter shows a reading of 10 ampere. So the reading of the test ammeter shall be referred as IM, measured value of the current passing through the circuit. Now corresponding reading of the reference or standard or the substandard ammeter is also noted. We shall treat it as IS, true value of the current passing through the circuit. Now the current is decreased with the help of the variable load and approximately 5 readings of both the meters are noted. It is worth noting that in these 5 readings we shall include the maximum scale value as well as the zero value of the test ammeter. So we have two sets of readings: IM measured value, that is the reading of the test ammeter, and IS true value, that is the reading of the substandard ammeter. So error will be equal to IM minus IS. Percentage error will be equal to Im minus Is whole divided by Is multiplied by 100. So if you want to go further, you can plot a graph of percentage error versus measured value. This graph is known as calibration curve. Now we shall see calibration of voltmeter. Here also there are two voltmeters which are connected in parallel across the AC supply. Now we have used a potential divider to vary the supply voltage, since we will be taking approximately 5 readings of both the voltmeters. The first voltmeter is the test voltmeter, that is the voltmeter which needs calibration, which has to be calibrated. And the second voltmeter is the substandard voltmeter or reference voltmeter or standard voltmeter. Now the process is, with the help of potential divider, the supply voltage is adjusted till the test voltmeter shows its maximum scale mark, maximum scale reading. Say for example, if the test voltmeter has a range of 0 to 200 volt, then the supply voltage is varied till the test voltmeter shows 200 volt. So the reading of the test voltmeter shall be treated as Vm, measured value of the voltage. Corresponding reading of the reference or standard or substandard voltmeter is also noted, and that reading shall be referred as Vs, true value of the voltage. Now with the help of potential divider, the voltage is decreased and approximately 5 readings of both the meters are noted. Here also, in these 5 readings we shall include the maximum scale reading as well as 0 reading of the test voltmeter. So here also we have two sets of readings: Vm, that is measured value of the voltage, that is the reading of the test voltmeter, and Vs, true value of the voltage, that is the reading of the substandard voltmeter. So error is equal to Vm minus Vs. Now percentage error will be equal to Vm minus Vs whole divided by Vs multiplied by 100. Here also you can plot a graph of percentage error versus the measured value, which is known as calibration curve. Now we shall study the ammeter and voltmeters calibration as per Indian standards, that is the IS. Now as per Indian standards, the percentage errors formula is Bx minus Bt whole divided by At multiplied by 100. So here we have three new terms: Bx, which is reading of the meter under test; Bt is the reading of the reference or standard or substandard meter; and At is the fiducial value. Now what this fiducial value is? In simple terms, it is the base value which has been treated as the base for this measurement. Here our base value is true value, because we are calculating percentage error with respect to the true value. So here our fiducial value will be the true value of the current as well as voltage for ammeter and voltmeter respectively. So in case of ammeter, Bx will be equal to Im, Bt will be equal to Is, and At will be equal to Is. So for ammeter, we will have percentage error equal to Im minus Is whole divided by Is multiplied by 100. Similarly, for voltmeter, we shall have Bx equal to Vm, Bt equal to Vs, and At equal to Vs. So here also percentage error will be equal to Vm minus Vs whole divided by Vs multiplied by 100. Now the error can be positive or negative or zero. If the error is zero, it means that the reading of the test meter is exactly equal to true value of the quantity being measured. If the error is positive, it means that the test meter gives a higher reading than the actual value of the quantity being measured. Similarly, if the error is negative, it means that the test meter shows a reading which is less than the actual value of the quantity being measured. So, error can be positive, negative as well as zero. Now, we shall study calibration of wattmeter. Now, in wattmeter, there are two coils. First one is the current coil, and second one is the pressure coil. The current coil is always connected in series with the load, while the pressure coil is always connected in parallel across the supply. So here also we have two wattmeters. First one is the test wattmeter and the second one is the substandard or reference or standard wattmeter. Now the current coils of both the wattmeters are connected in series with the load, while the pressure coils of both the wattmeters are individually connected in parallel across the supply. Now here we have a provision of varying the load as well as the supply voltage. So for that, variable load has been used and a potential divider has been used. Now the procedure is the current and the voltage are so adjusted using the variable load and the potential divider respectively that the test wattmeter shows a reading equal to its full scale reading or maximum scale mark. Say for example, we have a test wattmeter of 0 to 1000 watts. Then in that case, the current and voltage are varied till the test wattmeter gives a reading equal to 1000 watt. So the reading of the test wattmeter shall be treated as Wm, measured value of the power. Corresponding reading of the substandard wattmeter is also noted, and that reading is referred as Ws, true value of the power. Now you can decrease current or voltage or both, and in this way, by decreasing current or voltage or both, 5 readings minimum are taken of both the wattmeters. Here also we shall include 0 reading as well as maximum reading or full scale reading of the test wattmeter. So here also we have two sets of power readings. Wm, that is measured value of the power, that is the reading of the test wattmeter, and Ws, true value of the power, that is reading of the substandard wattmeter. So error will be Wm minus Ws, percentage error will be Wm minus Ws whole divided by Ws multiplied by 100. Here also if you want, you can plot a graph of percentage error versus measured value, which is, as you know, known as calibration curve. Now we shall study calibration of single phase energy meter. There are three methods of calibration of single phase energy meter. The first one is long period dial test using substandard meter. Second one is short period disc speed test using substandard meter. The third one is testing using substandard indicating instrument and a stopwatch. Now the circuit for all the three methods are common. It is shown in the slide. The current coil of both the energy meters are connected in series with the load and their pressure coils are individually connected in parallel across the supply. Now we shall study all three methods in detail. The first method is long period dial test using reference or standard meter. Now as the name suggests, long period, in this test both the meters are run for a minimum of 2 hours. After time greater than 2 hours has elapsed, readings of both the meters are taken. If the reading of the test energy meter is EM, reading of the substandard energy meter is ES, then error will be equal to EM minus ES. Percentage error will be equal to EM minus ES whole divided by ES multiplied by 100. Now there are two limitations of this method. First one is that this method is costly. Second, it requires more time. So this method of calibration is not popular and is not widely used. We shall move to the second method. Short period disk speed test using reference or standard meter. The circuit is same as the first method. As the name suggests, short period disk speed test. So this method is carried for a shorter period of time, and here instead of measuring the energy measured by the energy meters, we shall be measuring the speed of their disks, that is the number of revolutions made by their disks. If the meter constants of both the meters are km and ks respectively, unit will be revolutions per kWh, kilowatt hour. Kilowatt hour is the unit of energy. And if the respective number of revolutions made by their disks are Nm and Ns, then from the value of meter constants and number of revolutions made by the disk, we can calculate energy measured by the energy meter. So for test energy meter, Em will be equal to Nm by Km, and for the reference energy meter, Es will be equal to Ns by Ks. So error will be equal to Em minus Es. Percentage error will be equal to Em minus Es whole divided by Es multiplied by 100. We shall move to the third method. Test using reference or standard indicating instrument and a stopwatch. This method is different from the first two methods. How? In the first two methods, we are using energy meter as the second meter, that is as the reference or standard or substandard instrument. Energy meter is a type of integrating instrument. So here instead of using energy meter, we shall be using indicating instrument as a reference or standard meter. Now we can use a wattmeter, or if you don't have a wattmeter, if you don't want to use wattmeter, you can use a combination of voltmeter and ammeter. But that those instruments should be substandard or reference or standard meters. So if we are using a substandard wattmeter as the second meter, then the circuit will be similar to the first two methods. That is, the current coils of both the meters will be connected in series with the supply, and the pressure coils of both the meters shall be connected in parallel across the supply. So if the disk of the energy meter is run for n number of revolutions, and the time taken by the disk to complete these n number of revolutions as measured by the stopwatch is t seconds, then the energy measured by the test energy meter will be n divided by k, where k is the meter constant of the energy meter. Now we won't be conducting or carrying out this test or this method of calibration for hours. We shall be carrying out this testing method for say few seconds or few minutes. Let's say we shall be carrying out this test for few seconds. So we need to convert the kWh into watt seconds. 1 kilowatt equal to 1000 watts and 1 hour is equal to 3600 seconds. So N by K kWh will be N by K multiplied by 1000 multiplied by 3600 watt second Ws. Now actual or true energy will be Es equal to W multiplied by T. W is the reading of the energy meter and T is the time as measured by the stopwatch. So error will be equal to Em minus Es. Percentage error will be equal to Em minus Es whole divided by Es multiplied by 100. Now as I told that in case you don't have a wattmeter, you can use a combination of voltmeter and ammeter. In that case, Es will be equal to V multiplied by I multiplied by T watt seconds. The circuit diagram, if you are using a voltmeter and wattmeter as the second meter, is shown here. Thank you very much for watching this video session.